Now that we've learned a little bit about stress, we can talk about simple design. And by that I mean the simplest way that we can make something safe. And the way we typically do that is with something called a factor of safety, or a safety factor, or allowable stress design. You might hear it by any of those names. But a factor of safety is this relationship between the stress allowed and the stress of failure, right? So simple design being, this is the minimum thing that we will allow so that we do not get a failure, right? Failure being, breaking or bending or something where it doesn't work anymore. So we can think about, if you look at your office chair, maybe, you'll notice that it has a little sticker on the bottom with a weight capacity on it. And maybe it says something like 180 pounds. That doesn't mean that a 200-pound person can't sit on that chair. It's just saying that the allowable weight that it has is this 180 pounds, and that the failure should be much greater than that, right? So there's usually a little bit of wiggle room. That's what this factor of safety does. It says, okay, we allow 180 pounds. A 200-pound person could maybe sit on it, but let's say it fails at 300 pounds. So if I have a 300-pound person sit on the chair, it breaks. That would mean that my factor of safety, we call this factor of safety, sometimes you'll see it abbreviated FS, that's usually how I do it. Factor of safety is this ratio of a failure, whoops, sorry, that's not the symbol I want, failure over the allowable stress, failure force over the allowable force, or failure stress over allowable stress. So if a 300-pound person sits on a chair and it fails, but the chair said the allowable stress, the little sticker on the bottom said 180 pounds, this would mean that my factor of safety of the chair, I gotta type this in, what is 300 over 180? Is 1.6. 1.67. So essentially it's a number rating that tells you how many times, it's like a multiplier, what the safety factor is in there. So it advises no more than 180 pounds, but it doesn't fail until 300. So your 200-pound person could continuously sit on this chair and still be safe, even though it's not technically in the allowable stress design. Right, so this is one of the simplest ways that we can design things. We can set an allowable stress that gives us this factor of safety wiggle room before something fails. So again, you'll see it listed as like this F failure, but we'll also see it with the stress, right? So the allowable stress, the failure stress, this is our normal stress, or can also be done with shear stress. Tau failure over tau allowable. Right, these are our factor of safety equations. We can use any of those. Your factor of safety is always going to be greater than 1, right? We always want the failure stress to be greater than the allowable stress. Otherwise, it's going to fail. So your factor of safety is always going to be greater than 1, but the most typical values are going to be like 2 to 3. This is usually an ideal design, so we're not over-designing it so that it's not too costly or too over-engineered. Usually about 2 to 3, a safety factor of 2 to 3 is ideal. Another really great thing that this allows us to do is calculate area required for a certain design. So let's say, for my normal stress, I have some rod like this, normal force on it. I can calculate area required using my normal stress equation. So there's my normal force over the allowable stress. right? That gives me an area required, where my allowable stress is calculated from that failure over whatever safety factor I want. So I can work my way backwards from this safety factor, because I'm going to know the failure and safety factor that I want to use, and I can work backwards to calculate an area required for my area, for my little cross-sectional area here. So that way I'm not exceeding the allowable stress. And same with my shear stress, right? I can have an area required for my shear and my allowable shear stress, where tau allowed is tau failure over that safety factor. That way I can know, oh, I need to use a 1/4 inch bolt in this design versus, versus an 1/8 of an inch bolt. I know that my minimum bolt size here would have to be 1/4. Like an 1/8 would be too small, an 1/8 would fail, or it wouldn't have a great enough safety factor. This gives us like a really basic template to use when we're designing things. Now, I will say this isn't the only thing that you have to use. There are other simple design, limited state design equations and things that you might see, especially in civil engineering. In civil engineering, there's this thing called load and resistance factor design. So LRFD is what it's abbreviated to. Load and resistance factor design. And this might just be a simple equation that gives different load values for different scenarios. Like one popular equation is R equals 1.2 D plus 1.6 L plus 0.5 S. So it's a very basic equation that takes a bunch of loads and adds them together for you so that you can use that as your basis of design. Where here, D is the dead load. So this would be anything that is from the structure itself generally. So if you're building a house, it would be like your timbers and joists and roofs and flooring and everything that goes into building that actual structure. Whereas, L here is your live load. And that would be accounting for things like weight of people, weight of furniture, beds, kitchen appliances, maybe anything that could be interchanged in the home that you still need to account for, but might be more variable than the actual load that's sitting there. And this equation even includes an S, which this is snow load. So whenever it snows, snow has a weight. It's a lot of water sitting on your roof that needs to be accounted for. And this would give you a load factor design. This is what this R is. We're not going to be using this or looking at this too much, but I do just want you to be aware that things like this exist, where instead of using a safety factor, you would be given a safety factor through a calculation like this, a formula that's pre-set up. It's a little more common in civil and structural kind of governmental work. But just be aware that it's a thing that exists. It's a thing that likes to pop up on the PE exam, which is why I mention it, or PE and FE exams. But it's really just you plug the numbers in and calculate. It's an addition equation. It's not too complicated. In this class, we'll pretty much be looking at these factor of safety calculations. So let's do that. Let's look at an example. So in this example, we have an eye bolt that's used to support a load of 5 kips. It asks us to determine diameter D and required thickness H of that support so that the washer won't penetrate or shear through, and then gives us an allowable normal stress of 21 KSI and a shear allowable stress of 5 KSI, and round to the nearest 1/8 inch. So it's a lot of information, right? It's a big block of text that they throw at you, and you have to kind of just pick out what the most useful pieces are, or if there are any useful pieces to you, and work from there. Even if you aren't sure on how to approach something like this, maybe you don't know what equations you need to use, go ahead and just write out everything they give you, right? So I have an allowable stress, right? Allowable is 21 KSI. Allowable shear stress is 5 KSI, and they give me that 5 kips. So that load there, that force, the force is 5 kips. So if I'm thinking about how I might want to approach this, I would probably go back and look at my equations, and knowing that I have to find this diameter D and thickness H, I'm going to want my area. So we can go back to our equation that we just had, right? Our area required. This is what we're finding, really. We're finding diameter required, but we can find that from area required. So we had that area required equation for our normal stress anyways. Area required is the normal force over the allowable stress, which is really great because we have the allowable stress and we have this normal force, right? If we were to look at the cross section here, we were kind of to snip this, a section of this eye bolt, what we have is we would see the 5 kip force running through it, and then we would see the cross-sectional area here is made up of this by this diameter D, right? Area here is the area required, and that we can represent as pi over 4 D squared, where we're trying to find that diameter, right? And my 5 kip is my normal force. So I can pop these puppies right into my equation, right? Pi over 4 D squared, we said that's my area required, equals that normal force, right? The force axially through my eye bolt here is the 5 kips over the allowable stress they gave me is 21 KSI. So I know that when I divide this out, I'm going to get my diameter in inches, in square inches, and take a square root. So my diameter, if I go ahead and do the math, punch all this into my calculator, move that pi over 4 term over, take the square root, pop it into my calculator, I get 0.551 inches, right? Just straight from the calculator. Now, remember, that's not my final answer. It did say round to the nearest eighth, which makes sense, right? If you're going to order a bolt, you're not going to order a bolt that is exactly 0.551 inches. You're going to have a really tough time finding that. We don't want to special order any bolts. So we're going to go to Home Depot, round to the nearest inch. And in this case, do we round up or down? Right? So our two nearest are 4/8, of course, is 0.5. So that would be a 1/2 inch. Or the next eighth is 0.625, which is 5/8 of an inch. So which one of these do we go with? You might think the 0.5 is technically closer, right? It is technically nearer to 0.5 than it is to 0.625. But this is a minimum required diameter. This is going to be a minimum required diameter for us. Right? The area required so that we hit this allowable stress. If we do an area less than that, then we would get closer to a failure stress. So this is a minimum diameter for us. We're always going to want to round up. Even if our diameter D here was 0.501 inches, I would still recommend rounding up to the 5/8 inches. Just you have that extra safety factor in there. Right? So this D is a minimum. So if I were to place the bolt order, I would go ahead and put in my eye bolt as a 5/8 inch. Right? As engineers, we do actually have to think practically about these things, right? We don't want to be putting in specialty orders. We want to think about what's actually happening in the real world. What can I get? And here it's going to be a 5/8 of an inch eye bolt. So that's the first part of our question. We found our diameter D, but now we want to find the required thickness H. And this is a little tougher, right? We know we're going to be working with our allowable shear stress here. That's the other thing that we have. But where is it shearing? If I were to draw this out again, where is the shear occurring? If this thing is going to blow through H, right? We want to prevent the washer from penetrating through, right? We don't want this to come through this thickness H here. We have to find how thick we need to make this. Now, in this case, your shear is not like your axial one, right? Your shear is happening on this plane where the surfaces are kind of rubbing against each other, right? That's where our shear is occurring. Our shear is always happening along the same side. Draw it like this, right? You'll recall when we were dealing with shear, we would say, all right, if I have these bolt here where these two interact, my shear is happening in the same plane as the area. So here my shear is happening in this washer, right? So this is trying to push down. This is my 5 kips is pushing down. And so we're going to see it all along the circumference of the washer. Kind of draw this in a 3D form. So we have that. This thickness H kind of goes back like this. We have the washer on top. A 1-inch washer. And then here's the nut for the bolt that goes down. The shearing is where this washer would be going through the thickness H here. If you can visualize that, if that kind of makes sense. It's this cylinder, right? As if it were pushing through this distance H. It's where those two surfaces would be rubbing against each other, interacting. Because this 5 kips is still acting in the same place in the same way, right? So it's still acting down through this, down through the eye bolt, and the shear is occurring along the edge of the washer, where it would be trying to shear against the internal material of H. So what I'm going to have there, write out my area required for shear over shear allowable, where again, now my shear is the 5 kips, and they gave me the allowable shear stress was it 5? Yes, 5 KSI. Now the area that we're dealing with is this cylinder here, the cylinder with a height of H and the washer dimension of 1 inch across. That's where the shear would be occurring. So what I'm going to need is this area here. It's actually the area around the cylinder. So my area is going to be the circumference times H. Circumference is pi r H, or in this case pi dh. Pi dh. That's my circumference times the height. Gives me the round area around that cylinder. Pi h. So I have pi times h. It's 5 kips over 5 ksi. So that my allowable height is 0.318 inches. And again, it says round to the nearest eighth, so even though I might be able to get this plywood board or whatever it is that the eye bolt is going through, I might be able to get that in different dimensions. It says round to the nearest eighth of an inch. So again, we're going to round up, right? This is a minimum dimension. So my h, what are my nearest ones? 1/4 would be 0.25. 3/8 is 3.75. So 3.75 is greater, so 3/8 of an inch would be the thickness required so that this doesn't shear down through that plywood or whatever it's bolted into, the concrete, whatever it is. It's that area of interaction, right? Just as we said, this bolt here is the area of interaction between these two boards, and we took this area. This area of interaction would be the sides of the washer. Side of the washer going through H. Let's take a look at one more example. So this example asks us to find the safety factor for each cable, given that we're holding up this 60 kilogram lamp with cables AB and BC. They tell us the cables have a failure normal stress of 8 megapascals. And that's really the only thing they give us. They give us a weight of a lamp, and they give us the failure normal stress. So we know our factor of safety equation. And we know that we're going to be dealing with normal stress because they gave us the normal stress failure. So we will need to find the normal stress allowable for the safety factor. Or in this case, what is the actual normal stress that's being experienced by each of these cables so that we can find out what the safety factor is. So for each cable, we're going to have to calculate the normal stress. Right? Our normal stress equation is that normal force over the area. And, oh, they do give us diameters. Sorry, I forgot to put these on here. They do give us that the diameter of AB here is 10 millimeters, and the diameter of BC is 15 millimeters. So that's good. That's important because we need that to calculate our area, our cross-sectional area for each of those. So we'll need to get our cross-sectional area for each of those as well as the normal forces. So our first step, as always, anytime we approach these problems, we don't have these forces. We only have the weight of the lamp. Free body diagram. Free body diagram, we know them, we love them. We have to do one to solve for what the force through cable BC is and the force through cable AB. Of course, we have that weight of the lamp. I'm going to skip over this portion because I feel like you're probably pretty good at statics at this point. You can set up and solve these equilibrium equations and, double check these. Check for yourself. But we have the force through AB is 474 newtons, and the force through BC is 296 newtons. Those are our forces, again, derived from the free body diagram and our equilibrium equations, just summing forces in the y direction, forces in the x direction. Those are the results that we get. So now I can use those results to calculate my normal stress for each of these. So for my normal stress in AB, it's going to be that 474 over the area, which is pi over 4 d squared. D is 10 millimeters for AB. That's 0.1 squared, just to get my units in newtons, and then this is unit in meters instead of millimeters. And that's going to give me a normal stress, if I punch that all into my calculator, of 6.1 megapascals. And then I do the same with the normal stress in cable BC. It's actually all through there, 296 newtons over pi over 4, 0.015 squared. And that gives me 1.67 megapascals. So it told me that my failure normal stress is 8 megapascals. 8 megapascals, which I gotta say is a little bit close to our AB guy here. It sounds like it's getting pretty up there. When I calculate this safety factor, the failure stress over the actual or allowed, in this case our actual stress is experiencing, is going to be 6.1. So it's 8 megapascals over the 6.1 megapascals gives us a safety factor, dimensionless safety factor, of 1.3. And that's for cable AB. Go through the same process with the other one. Our failure over the allowable is 8 over 1.67. Gives us a safety factor of 4.8. Now that one's looking a lot more comfortable, right? That's a lot better. This tells us that we should really be watching out for cable AB. If a strong wind goes by, or if the force changes, if we get a heavier light bulb or replace the lamp with a heavier lamp, then we'll know that our cable may not be sufficient, right? If the lamp is too much heavier, we already have a kind of low safety factor on that it's much more likely that cable AB would fail before BC. And we might intuitively know that just because the diameter of AB is smaller than BC. But here we can show it, and we can show that just that increase in a 5 millimeter difference in diameter, right, a 50% increase in diameter gave us up from 1.3 to 4.8, like a triple, quadruple increase in safety just from that minuscule change. So those are the things we kind of keep in mind as we're doing design, is we want this buffer in there. We want this factor of safety just so we don't get too close to failure. We don't want to be near that failure point, because any gust of wind, any minor change could cause you to accidentally hit that fail point. You want that wiggle room in there.